Welcome back to CE Masters. In this lecture, we are going to discuss regarding single degree of freedom system. Okay, what is the single degree of freedom system? If you see here, a system having only one single coordinate available to describe the position of the mass, okay, the motion of the body. We have only one direction, one coordinate, one single coordinate, either x or y or z or rotation. Okay, we have only one degree of freedom system, means there is availability of position, availability of coordinate which mass can be displaced from its original position. Okay, that one we used to call as the single degree of freedom system. The simplest vibratory system can be described by a single mass connected to a spring and possibly a dashpot. The mass is allowed to travel only along the spring elongation direction. Okay. Such systems are called single degree of freedom system and are shown in the following figure. If you see this figure, the mass has been connected with the two parameters, two elements. One is the spring, another one is the dashpot. Okay, dashpot provides the damping to the system. Okay, spring and dashpot. And this body is free to move in only in one direction. Okay, force has been applied in one direction, in the direction of x. In this direction we can see the displacement of body in x direction. Okay, this type of system we used to call as the single degree of freedom system. The motion of the body can be uh, available in only one direction. Okay, if you apply force in x direction, the body motion will be in only in x direction. Okay, that one is called as the single degree of freedom system. From this single degree of freedom system, we used to derive equation of motion of single degree of freedom system. Okay, equation of motion for single degree of freedom system. If you see here, okay, if you draw, if you take this single degree of freedom system, okay, and if you draw the free body diagram for this particular single degree of freedom system, you can get diagram like this. And single degree of freedom system, single degree of freedom vibration can be analyzed by using Newton's second law of motion, which is nothing but force is equal to mass into acceleration. The analysis can be easily visualized with the aid of free body diagram. And here as well as we can see the moment, inertial force also. Okay, there will be two things will be there. This system can be derived like this. Stiffness, the relation between stiffness and displacement we can see here. Force is nothing but stiffness and displacement. And similarly here, dashpot and velocity. Okay, these two parameters will resist the force which are applied over this particular body. Okay, the force, total force F of t is taken by these two materials. Okay, and other parameter also, their mass also going to take some of the force, some amount of the inertial force. This one from sorry, some inertial force also can be applied over this particular body. Okay, whereas mass will be moves in downward direction because of the motion of mass. The inertia will be developed in opposite direction. If you see here equation k, if, this one is the free body diagram, whereas displacement of the body in the direction of x, we can see here. Here we have taken displacement of the body as x. X is the displacement of the body. Then inertial force, the force resisted by the mass. We can see here force resisted by mass, which we used to call as the inertial force, is equal to mass into acceleration, which is nothing but m into x double dot. And spring force, the force taken by this spring can be taken as Fs is equal to k into x, stiffness into displacement. Similarly, damping force also can be taken by dampers, this dashpot. That one can be calculated, that one is calculated by using f of d is equal to c into x dot. Okay, whereas the damping constant into velocity. This one c is the damping constant, and x dot is nothing but velocity of the material, that is element. Using Newton's second law of motion, we can formulate the equation force is equal to mass into acceleration, whereas force is applied in one direction, mass has been applied in another direction. And force parameters we can write here, whereas the force parameters minus kx minus cx dot are in negative x-axis direction, whereas force in positive x-axis direction. And these two are equal to the mass resist inertial force. Sum of these forces will be equal to the inertial force. Okay, m into x double dot. The resulting equation of the motion is a second order. We can see the x, whereas we can see displacement, double derivative of second derivative of displacement we can see here. Okay, the motion is second order non-homogeneous ordinary differential equation. We can see here ordinary differential equation, and this equation can be written as m, if you take these two negative signs towards the positive direction, then we can get the equation like this: m dot x double dot plus c into x dot plus k into x is equal to f of t, whereas m inertial force is there, and damping constant into velocity will be there, and displacement into stiffness of the body will be there. These three will resist the total force which are coming over the particular body. Okay, this condition we used to call as the equilibrium condition. Okay, dynamic, this equation is called as the, here we can see components of the forces. Here these forces has been resolved in this way, whereas inertial force, which is nothing but mass into acceleration, and spring force, which is nothing but stiffness into displacement, damping force, which is nothing but Fd is equal to c into x dot, whereas damping constant into velocity of the body. Okay, this is regarding the body forces, means free body diagram of given dynamic system, given mass, spring and dashpot system. Using Newton's second law of motion, we can derive this equation: force is equal to mass into acceleration, whereas minus kx into minus cx dot plus f of t is equal to m into x double dot. The resulting equation of motion is a second order non-homogeneous ordinary differential equation. Now for the equilibrium condition, we can see there equation of single degree of freedom system: m into x double dot plus cx dot plus k into x, which is equal to f of t, whereas f of t is nothing but external force applied over that particular mass. If you take f of t is equal to 0, means that then the equation will becomes m x double dot plus c into x dot plus k into x is equal to 0. In the place of f of t, we used to apply 0. This condition we used to call as the free vibration of the body, free vibration condition. Whereas another one is there, force won't be equal to 0, force is not equal to 0. Okay, in case of forced vibration, force will be there, we are going to apply force, there won't be 0 in the force. Okay, if force is not equal to 0, then we used to call it a forced vibration system. Further, we can say when the body is having, whereas c is the damping constant, if you make c is equal to 0, the system is called as the undamped vibration system. Okay, then the equation we can formulate like this: m into x double dot plus k into x is equal to 0. Those type of equations we used to call as the undamped free vibration system. For undamped condition, equation will be there, c will becomes 0. Okay, if a force is 0, then free vibration system with undamped vibration. If c is not equal to 0, this equation is called damped forced vibration system, whereas c is not equal to 0, this is damped system. Whereas if you make c as 0, this is undamped free vibrations, forced vibration system. If you make force as 0, then we used to get two conditions: damped free vibration system and damped free vibration system. These are the four conditions which we used to use in solving dynamic equation of motion. Okay, this particular system we can idealize like this, whereas in structural case, in our case, we can make a slab, rigid floor is there, that one we used to take as mass of the system, whereas columns are made to take stiffness to carry the stiffness, and here we used to make columns to carry the stiffness. Okay, and material property, damping of the material, okay, we used to call as the dampness of the system. Okay, this one is the idealization of the building frame with respect to in terms of mass and stiffness, whereas x of t is taken as the displacement of the body, and this can be idealized like this. For this particular system we can draw equivalent spring mass system like this. Okay, spring is there, mass is there. Spring indicates the stiffness of the columns, whereas mass indicates the weight of this particular mass of this particular slab, and this can be written as like this: equivalent spring mass system. Okay, this is regarding single degree of freedom system.